should just start right off. So, John Baker, University of Michigan Philosophy Department, Broken Symmetry and Spacetime.
Thanks, Will. All right, good morning. And I want to say also I'm very honored to be here. Very excited about this conference. It's going to be cool. So this talk is going to focus on sort of apparent inconsistent triple that I've come across in looking at symmetry breaking in the algebraic approach to quantum field theory. So some of these terms up here will admit of more precise definitions or explicit definitions as I go on. But the trilemma, as I'm calling it, the first part of it is that, well, in 2001, Hans Halvorson and Rob Clifton proved a theorem that they interpret as saying, well, if I take two unitarily inequivalent representations of quantum field theory, remember that term because it's going to come up again, the folia, that is the states associated with those two representations, are physically equivalent only if they're unitarily equivalent. And unitarily inequivalent representations are physically equivalent. That's the sort of technical part of the trilemma. The other part is one that's become very familiar with work on the whole argument in general relativity, and in general with the way people think a lot of the time about space-time symmetries these days. It's a view that I hold, and I think a lot of people also hold, both on the substantivalist and relationist side of the divide. The view is that global space-time symmetry transformations, and those could be diffeomorphisms in general relativity, or they could be things as simple as the examples that Leibniz used to work with, where he said, imagine everything in the universe translated 5 feet to my left, or imagine everything in the universe boosted to a velocity of 1 meter per second faster in that direction. That these global space-time symmetries don't relate distinct physical possibilities. They just correspond to unphysical changes in coordinates, or things of that sort. And they're just ways of re-describing the same possibility over again. The third part is, and this is going to become interesting when we do the breaking of space-time symmetries. The third part is that in the algebraic approach to quantum field theory, if I have a situation where a symmetry is spontaneously broken, then the different outcomes of the symmetry breaking, that is, the different possible ground states that the system could take on, they live in unitarily equivalent representations. Okay? And it's going to turn out that when space-time symmetry is broken, these global space-time symmetries, which look like they should never relate distinct physical possibilities to each other, are nonetheless going to relate states that live in unitarily inequivalent representations, which by the first point in the trilemma, it looks like they should be physically inequivalent. Okay, most of the talk is going to be expanding on this trilemma, so if you don't get it yet, that's cool. You will, I hope. So, spontaneous symmetry breaking. This is where the whole thing started. The notion of a symmetry in physics, right? Of course, here's a property that a geometric square with 4 indistinguishable points has in common with Newtonian physics. If you perform a 90-degree rotation on it, it doesn't change the square. You have a qualitatively identical square. Similarly, if I take a solution to Newtonian physics, like where I'm dropping, my water bottle,
Put the cap on.
I'm just illustrating with a hypothetical, although I'm sure it'll happen at some point soon. I'm pretty clumsy. If I drop the water bottle, I want to take that whole situation, myself, the water bottle, all the objects that are related to us by Newtonian gravity, and rotate it 180 degrees. That's going to give me another solution, just the same as the one I had in the first place. And we may say, for the purposes of physics, qualitatively identical. Right. So in that sense, Newtonian mechanics, like the square, admits a symmetry of 90-degree rotations. You can perform those to the solutions of the physics without changing the physics, is the tagline. And there are ways of making this precise. Symmetry breaking, as we call it, occurs when a state doesn't share some symmetry of the laws. And almost every physical object you encounter in everyday life is an instance of symmetry breaking. Like for me, you know, I look a little bit left-right symmetrical, but actually my heart is on the left side of my body. And if you do a mirror reversal of me, that would change my physical makeup. But the physics, well, the most fundamental physics looks like it's not mirror symmetrical. But if I were a Newtonian human being, then the physics governing me would be left-right symmetrical, and it would, you know, I would break that left-right symmetry of the physics. Spontaneous symmetry breaking is the situation that's really much more both physically and philosophically interesting because it's much less commonplace, right? It's a situation where not just as any old state, right? So I'm not a ground state. I've got all sorts of energy, as you'll discover in the course of the talk, right? But spontaneous symmetry breaking occurs when you have a privileged state that is a ground state of lowest possible energy, which doesn't share some symmetry of the physical laws, right? When that happens, of course, it's going to be legal to apply a symmetry transformation like one of these rotations to that ground state. And when that happens, it's going to just give us back another ground state because it's not like a symmetry transformation is going to change how much energy something has. So, in a sense, we're going to say there are multiple ground states, and which of them occurs is going to depend on initial conditions. That's an idea that we're going to have to question, by the way, when we get into talking about space-time symmetries and their breaking. So hold on to that thought. So here's an example of broken space-time symmetry, spontaneously broken space-time symmetry. If you set up a sombrero, right, people often talk about these quote-unquote Mexican hat potentials in field theory, but of course you could just say, look, I'm taking a physical sombrero and putting a physical ball on it and having the ball constrained to move on the surface of the sombrero, and having the whole system governed by, you know, Newtonian gravity with just a gravitational constant pulling us this way, right? Well, what are the ground states for the ball hat system going to be? What are the states of lowest energy going to be? Not the ones where the ball is rolling back and forth like you see here. They're going to be the ones where the ball is perched down on the bottom of the brim of the sombrero. So total energy is minimized by any state like that, right? It's not like being here along the bottom of the brim has a different energy from being here on the bottom of the brim. So I'm going to have multiple ground states which are related by the rotations I can do to move the ball around the brim of the sombrero. Okay, so that's the basics of spontaneous symmetry breaking, including space-time symmetry breaking. Let's talk about Leibniz equivalence, right? This is the principle that space-time symmetry transformations don't give us new physical possibilities. Well, if I do a symmetry transformation to some space-time theory, as I was saying before, it looks like it amounts to a change of coordinates. Or, if you like, you know, we talk about taking a system and changing its global position. Do I rotate it by some angle? Do I translate it over 5 feet or something like that? Do I change its global velocity? And plausibly, it looks like these changes in the global position or velocity in a system, unless it's angular velocity, right, which is going to give us some acceleration. It looks like these changes, these global changes, aren't real physical changes, right? When you think, could the universe have been a universe in which everything was just the same except we were 5 feet over that way? Well, I don't know. You know, there's no qualitative difference between that universe and the one that we live in, right? Why should we assume that those are different possibilities? Physics, we might think, is concerned with qualitative features of reality. And to talk about distinct physical possibilities that have all the same qualitative features in that case looks like a mistake. Also, I mean, suppose that I grant this, right? Well, that amounts to denying. Suppose that I grant that, for instance, all the states of the ball along the brim of the sombrero are really the same, right? Because they're all related by global rotations, which don't change anything. Well, what that amounts to is denying that the parts of space-time, that is either points or directions in space or something like that, have primitive identity from world to world, right? I'm saying, look, it's not like there's a separate possibility where the ball is rotated 30 degrees from where it actually is. In some ways, the point at which the ball is at, right, its identity is fixed by its relationship with the physical objects, the ball and the hat. And that doesn't change when I go from one ground state to another. And if we don't deny that the parts of space-time have primitive identity, then, and this has become a very powerful motive for people to deny that the parts of space-time have primitive identity, we run up against the whole argument, and it seems to show that general relativity is indeterministic in a strangely unobservable way. A lot of people don't like that result and see it as a reductio of the idea that points in space-time or parts of space-time have primitive identity. Okay. Now, what we want to do is say, look, there's nothing wrong about our physical description of the sombrero and ball system in which there's spontaneous symmetry breaking and quote-unquote multiple ground states. We want to square that with this idea of Leibniz equivalence. Well, suppose that the system of the sombrero and the ball is alone in an otherwise empty world, right? In that case, there's not going to be any qualitative difference between the ground states that I get by rotating the ball along the edge of the sombrero. The only qualitative difference between the points along the brim is where they're located with respect to the ball. Otherwise, they're all identical. So, if these ground states are distinct possibilities, it must be because those points have some kind of primitive transworld identity that tells you, look, this is the point that the ball is at in the actual world, but it might not have been at that point. Okay. Now, of course, Leibniz equivalence makes us want to deny that points have primitive identity from world to world like that. So if we accept Leibniz equivalence, all the ground states of the ball hat system have to represent the same possibility. Okay. Well, we want to say that two ground states of the ball and hat system in classical physics are physically equivalent. That can't be the case, we might think, unless they're intertranslatable in the following way. Right? Take the set of states that I can reach, supposing the symmetry is broken in one of those possible ways, by some particular angle going down the hat. Right? Taken, in a sense, the set of excited states that I can get from a ball that has fallen down to one particular point in the hat, and compare those with the ones that I can reach from another point on the hat, where the ball might have rolled down. What I need is a bijective map between the states that go along with one of those results of symmetry breaking and the observable quantities that are defined on those states. That preserves, first of all, what physical quantities are denoted by those observables, right? So we want to make sure that we're still talking about describing the same qualitative properties of the system. Okay. And second, we want to hold on to the values that those quantities take on in each state. So if by rotating the ball around the hat, I changed the charge of something or other or the mass of something or other, then I would have a qualitative difference between my two worlds, and I wouldn't be happy with that. Luckily, in classical physics, it's really trivial to show that if I do a coordinate transformation, take theta to theta plus whatever this epsilon is that I get when I rotate the ball hat system in polar coordinates, it'll just take care of it. It's no problem, right? I have obvious intertranslatability between my different states of my classical symmetry breaking system. The problem is going to be when we get into quantum theory, and we're going to find that it's very difficult to say that if I had a quantum ball hat system and it had infinitely many degrees of freedom, it's going to be very difficult to say, well, I can translate between the states in which the ball ended up along the plus z-axis and the states in which it ended up along the plus x-axis. Okay. Well, I'll get into that in just a second. So, language and quantum theory, right, many of you will be familiar with this. We represent a state of affairs by a vector psi in the space of possible states, and a physical quantity is given by an operator that is a map from vectors to vectors on that state space. It takes psi to another vector, a psi. And if I want to know the expected value of a in the state psi, I just take the inner product of psi with the vector that I get when I hit it with a. Right? And of course, all these things are also true under eccentric descriptions of classical physics. We want to make sure we're talking quantum physics. So we impose commutation relations on our canonical observables, the position and the momentum, so that we require that the uncertainty principle holds. Now, when we do that, our state space becomes a quote-unquote representation of the commutation relations. That just means that it satisfies the commutation relations that tell us the certain units. And if we have a finite number of degrees of freedom, that's where we stop. But if we have an infinite number of degrees of freedom, as occurs in quantum field theory or in the limit in quantum statistical mechanics, then, okay, like I just said, we're working in a Hilbert space representation of the commutation relations. Well, when I have infinitely many degrees of freedom, there are uncountably many representations of the commutation relations. Each of them has a folium, that is, a family of states that I can use density operators in that Hilbert space to represent. Right? And we use the word unitary equivalence to describe our criterion for same representation. It means there has to be a unitary mapping between the two Hilbert space representations. If there's not, then we'd say they're not the same representation. Right? Well, in some cases, it looks like the difference between inequivalent representations is how did some physically contingent matter of fact work out, right? And symmetry breaking is going to be a paradigm case like this. It's going to turn out that depending on how the symmetry is broken, depending on which direction the ball rolled down the path, right, we're going to end up in different unitarily inequivalent representations of the canonical commutation relations. Okay. Interesting question, and a question pioneered by my colleague Laura Ritchie, is how do we physically interpret the existence of all these inequivalent representations? Despite the fact that they satisfy the same commutation relations, right? The inequivalent representations don't share all of their observables, only some. There are observables shared in common by all the representations. They're located within what we call, in the boson case, the Weyl algebra W, right? And I'm going to just use that to refer to the algebra of observables for whatever system we're talking about, right? There's this invariant algebra of observables, which is shared in common by all of the Hilbert space representations of a given set of commutation relations. And you might think, well, here's a view that I could hold about this, is that the only fundamental quantities are the ones that are invariant under that switch from representation to representation, right? Because, you know, why should I allow these representations to tell me what the physical quantities are? I'm going to just define the physical quantities as the things that don't change when I switch from representation to representation. And you can call this conservatism about observables, right? Because you're saying, I'll only allow a few of those guys in, just the ones that don't change when I switch representations. Problem is, that excludes some really important looking observables, and this is the thing that Laura in her work has done an excellent job of stressing. The stress energy tensor is one of those. We like to think that's pretty important given it's the source of the gravitational field in our best theory of gravity. Temperature is another thing that we like to think does a lot of good work explaining things in quantum statistical mechanics. More debatable cases are things like how many particles there are. That's debatable because the question of whether there are particles in QFT is such a vexed question. But still, looks like a really important observable prime equation, right? So, insofar as we think these observables are important things that really should be ascribed to the physical possibilities, that's going to point us toward this other view, liberalism, about observables. It says, look, some of the physical quantities are given by operators that aren't in this Weyl algebra W, but are parochial or local to one representation, right? If we want to say stress energy is real, then, well, there are only some representations where stress energy is real. We're going to have to restrict ourselves to those representations. Or say that outside of them, one of the fundamental quantities doesn't get instantiated or something like that. That's all by way of preamble to looking at what happens when we break a symmetry spontaneously in quantum field theory. Well, remember, symmetry breaking gives us at least formally multiple ground states that are all related by symmetry transformations, right? In quantum field theory, you can show, look, each representation has a unique ground state that is usually defined as a unique translation invariant state of lowest energy. So if we want to model and by the way, representation here for the cognoscenti, I'm talking about irreducible representations of computation relations. So we're going to need multiple inequivalent representations if we want to model spontaneous symmetry breaking accurately. The physically best known example of this is the ferromagnet. Right? If I take a magnet and set it up and cool it down as far as it can go, well, it's going to be polarized in one direction or the other. One end of it is going to be its north pole, and the other end is going to be its south pole. And the north pole is going to pick out a preferred direction, right? The direction in which its magnetization vector points. So that's a situation in which I have a physical quantum system. Okay, we have to, in order to get the fact that this symmetry breaking happens, we have to assume that the magnet is infinitely long, which is kind of weird, but, so what? When we do that, we get spontaneous breaking of rotational symmetry because we have a preferred direction in which the magnet's magnetization is pointed. Now, if I take a state of an infinite magnet like that, it's just sitting in a world by itself, and I perform a global rotation on that state, the result I get is a state in a different unitarily inequivalent representation. So the ground state is a magnet that, naively we might say, is pointing along the plus z axis, lives in a unitarily inequivalent representation from the ground state that's pointing, we might say, in the plus x axis. So this is the qualitative difference between classical and quantum symmetry breaking that seems to lead to an apparent failure of physical equivalence between the states that point along plus z of the magnet and the states that point along plus x of the magnet. I reserve the right to change my axes, by the way, while I'm talking to you guys. This might become the plus x's. Let's see. So just go along with my transformations here. We want a way to intertranslate the states along plus x and the states along plus z. See there, I just did it. Right? We want a way to say, look, these states are physically the same possibilities as these ones, or else we might have to ditch Leibniz equivalence. Now we need that. The problem is that translating between different inequivalent representations in quantum field theory gets really hairy. So we would think, well, look, take the model or the bunch of states that contains the excited states and the ground state pointing along this direction, and the one that contains the states pointing this direction. Okay. Well, they're physically equivalent only if, like we saw in the classical case, I can make up a translation scheme between them that's going to show that my observables represent the same physical quantities in both cases and that they give the same predictions about those quantities. We might need more things, right? This is an only if. They'll be physically equivalent only if I can make up this translation scheme. What this requires, yeah, just like I said, we have to map the physically significant quantities and the predictions about their values from the one situation into the other, from the plus x situation to the plus z situation. Well, in quantum field theory, our physical quantities are given by operators and our predictions are given by states, which tell us what the expectation values for those operators are. So, since a representation picks out a distinguished set of operators and a distinguished set of states, which we call the folium of the representation, we can indeed ask, are two representations intertranslatable? Okay. Now here's what Halvorson-Clifton claimed to have shown. And I say claim because this will become interesting. They say, assuming liberalism about observables, this is that great view that tells us that the stress energy is real and not fake. Right? So we like this view to start out with. We have an initial bias towards this view because we have an initial bias that, yes, there is a stress energy tensor in the world. Assuming this liberalism view, then there's a translation scheme between two irreducible representations, they say. That is, between the representation where the magnet is polarized along plus x and the representation where the magnet is polarized along plus z. There's a translation scheme between those two representations only if they're unitarily equivalent. Well, the problem is they're not unitarily equivalent, right? That's what has to happen when you break the symmetry. So, does this mean that when I take rotate that by some angle, I'm generating a physically different situation, according to the liberal. Well, I'm generating a new inequivalent representation, one that's inequivalent to the one I had in the first place. So this result looks like it entails that I'm producing a new physical possibility, because I'm producing, when I take the states, the bunch of states pointing along X, and I rotate them all, I can't translate between those two bunches of states. That's what Clifton and Halvorson say that they've shown. If this is right, we have to either take the unattractive step of denying liberalism, or we have to accept that quantum field theory gives us new reasons to deny Leibniz equivalence that we didn't have. And if you go down that road, you might have to deny Leibniz equivalence, which I find unattractive, although I have colleagues who don't find it as unattractive. One thing you can think is that there might be a metaphysical fix available that's going to allow us to square these results. And it may be that there is one. So this is inspired by some work actually that Nick Huggett, as well as Oliver Cooley and Carl Hiffer have done about how to square with the idea of Leibniz equivalence the fact that there is parity asymmetry in some fundamental laws that we see in the weak theory, in quantum field theory. So these brilliant guys have figured out how do we preserve this idea that global space-time symmetries don't generate new possibilities in the face of the fact that in the weak theory, it looks like the laws discriminate between right and left-handed times. Right? How do they do that? Well, strictly speaking, what has been realized is that the theory can't really be treating right and left-handed particles differently, because the way the handedness of particles is defined is relative to a conventional right-hand rule that tells us when we do cross products, right, we have to, the cross product vector of two vectors points along the thumb of your right hand, right? When you learned electricity and magnetism in the first place, they taught you this right-hand rule. Well, they could have taught you a left-hand rule. It's just a matter of convention. And if they had taught you a left-hand rule, then we would have a different definition of which particles are right and left-handed. So, it looks like there's a matter of convention that comes in, and that can't be of any importance to the physical laws. If I want to hold on to Leibniz equivalence, what I can maintain is that although there's a preferred handedness to the world, according to the weak theory, it's not like there's a primitive matter of fact about whether it's right or left-handedness that's preferred, right? Because which handedness is right-handedness is a matter of convention that we set. It's just that there is a preferred handedness. And, a particle either has that preferred handedness or it doesn't. So similarly, we can say, well, looking at this case of the infinite magnet, maybe it's just a case that there's a preferred direction that the magnet can point. And a magnet could either have that direction or not. If it doesn't, it could be related to that direction by some angle. And that's going to be a way of showing why is it that we represent these states related by rotations as being physically inequivalent. Some of them are pointing along the preferred direction, some of them aren't. Problem is, well, the reason that this worked so well in the case of the weak theory is that the weak theory isn't symmetric under parity switches. So to say there is a preferred handedness, that sounds perfectly square with the theory, right? That makes perfect sense. If the theory is asymmetrical with respect to parity, then what you're saying in effect is that there is a preferred handedness. But in normal quantum field theory, on Minkowski space, it's certainly not the case that the theory is asymmetrical with respect to rotations. We might have a broken symmetry. That's what it looks like a case is supposed to be about. But to say there is a preferred direction in Minkowski space, that's not very attractive at all. It looks like you're saying it's not just that symmetry is broken, but that there's asymmetry, rotational asymmetry, and that's extremely unattractive. So, despite the fact that the metaphysical fix would work in principle, I don't like it. I don't think it's very likable. It's not just that I don't like it. That's not my bias. I think there are objective reasons why you shouldn't like it. So, okay. we got all this way by accepting on blind faith, which is usually a really good idea, this thing that Halvorson and Clifton told us, right? Let's start questioning that, because it looks like it's led us down a blind alley. Well, there's a couple of things that they show in that part of their 2001 paper, and that paper is very long and rich. These are only a couple of the many theorems that they prove in that paper, and they're actually a bit isolated from some of the other results. But another thing they show in this same section is, okay, they've shown us, remember, that according to the liberal account of observables, representations are physically equivalent only if they're unitarily equivalent. They also show the same thing on the conservative approach to states, quote unquote, the way they define it. On the conservative approach to states, they say there's a translation scheme between two irreducible representations only if they're unitarily equivalent. Okay. What does a conservative about states say? Well, the conservative about states says, look, I've got all these representations in front of me, right? All these infinitely many representations of my commutation relations. And my view is, as a conservative about states, that all of the physical possibilities live in the folium of only one of those representations. Right? So the conservative is saying, look, all the possible states are given by my folium, and I want to know if that's the same folium of possibilities as this other inequivalent representation. And Halvorson-Clifton say, actually, looks like you can show that it's not. Right? So the conservative about states is somebody who narrows the possibilities down to the possibilities that live in just one of the representations. The thing that we've just discovered that I didn't point out to you before is that for Halvorson-Clifton translation, it's a relationship between exhaustive sets of physically possible states. So, you don't need to be, we might say, a liberal about observables, according to them, to say that the states of the magnet along plus x are physically inequivalent to the states of the magnet along plus z. Right? Because they say, look, a conservative about states, somebody who thinks that only the plus z states of the magnet are possible, would say, okay, let me try to make a translation scheme between my plus z states and the plus x states that this other guy is laying down before me. I can't do it, right? So it must be that those plus x states are physically inequivalent to my plus z states. Suppose you had somebody who was more liberal about states watching these two guys, sort of jaw on about this. He says, okay, these two guys are stupid about what states are possible, right? They're making a mistake in saying that all the possible states are in one folium. But they can't be making a mistake about whether the states in the plus z folium are physically equivalent to the states in the plus x folium. That's just a mathematical fact, that I can't make a translation scheme between those two bunches of states. Right? So this result couldn't hold unless two folia by themselves, considered as packets of states, are intertranslatable only if their representations are equivalent. Okay. Now that holds true independent of whether we're actually conservatives about states. The liberal about states, looking at these two guys from a God's eye point of view, would agree these states along plus z are physically inequivalent to these states along plus x of the infinite magnet. So it's not like ditching liberalism about observables is going to save us. It won't. Because anybody should look at the situation and realize, yeah, if the Halvorson and Clifton translation scheme is the way to go about things, the plus z states are physically inequivalent to the plus x states. No matter your interpretation of the observables, you will not be able to avoid this problem, if it's a problem. So it better not be a problem, right? I think that Halvorson and Clifton have included among their otherwise reasonable premises the following unreasonable premise. They say, look, when we're translating between two representations, we should do the following. think of the Weyl operators. That is, the operators that live in this Weyl algebra that's included in all the representations, right? The physical quantities that are held in common by all the different representations. They say, think of those as the primitives of our two theories, which are the representations, in analogy with the way the natural numbers can be regarded as the primitives of a theory of real numbers. Well, there's mathematically a lot of sense to that, right? Because we get the real numbers by taking limits of series of natural numbers. Similarly, we get all the other operators, or we can get all the other operators by taking limits of series of these special Weyl operators. So mathematically, there's a lot to what they're saying. Okay, but you might think, why should that mathematical property correspond to any kind of physical priority for the Weyl operators? I mean, maybe their invariance under changes in representation should give them some physical priority. That makes sense. But this feature that they generate all of the other observables, it's a mathematical property. I'm not sure I much care when I have my physicist hat on. But the main mistake they make is that they require, look, any translation scheme between two representations has to preserve the actual numerical expectation values of the Weyl operators, rather than, for instance, taking them to 5 plus the old numerical expectation values of Weyl operators, right? If I had a translation scheme that worked, except that it says, okay, every Weyl operator has its expectation value switched to the sign, right? If its original expectation value is +5, the new one's -5. Or if every expectation value gets bumped up by +1 or multiplied by 2 or something like that, Halvorson-Clifton would say that's not an allowed translation scheme. That's no good. Okay. Well, like I said, what privileges the Weyl operators? But the more important thing is, why do equivalent theories have to agree on the numerical values of the primitives? Why couldn't different numerical values in the formalism represent the same physical property, right? If I'm making a translation between two possibilities, and what it does is it switches charge to negative charge or something like that. Right? Well, that looks like it shouldn't be telling me anything different from the original thing. It's just that I've changed the sign that I'm using. And Halvorson-Clifton don't allow changes like that for the Weyl operators. I think that's an illegitimate assumption. And actually, in fairness, Halvorson agrees with me about this and has an errata that he's written for that paper. Luckily, there are many other results in that paper that are completely unaffected by the thing that I just talked about. So it's still a paper of great interest to the problem of whether there are particles in the quantum field here. Okay. Are we safe now? I'm worried that we're not. And this gets into the part of the paper that I don't have as well worked out, the speculative part. So we're questioning the Halvorson-Clifton result. And it looks like it hasn't stood up to that question. Right? How do we find out whether inequivalent representations of the commutation relations are physically equivalent? How do we find out whether the states in those representations are describing the same possibilities? Are we left adrift? Well, one thing we still have, which is definitely true, is Wigner's theorem, which tells us that only unitary mappings preserve all of the inner products between states. Right? Only if I have a unitary mapping between two Hilbert spaces am I going to preserve all of the inner products between the states that stand for the possibilities. And these inner products are usually given the handle transition probabilities because we use them empirically to predict how likely it is for one state to turn into another if we leave it out there and give it the time to quote-unquote quantum jump into the other state. Right? Does that mean that some state transitions are going to be more probable for magnets pointing along the plus z direction than they are for magnets pointing along the plus x direction? If that were true, it would be extremely bizarre. And it might be a reason to reject Leibniz equivalence, right? Because the direction the magnet is pointing might be doing some work towards telling you how likely some of these state transitions are. Or it might be a reason to adopt this bizarre metaphysical fix according to which there actually is a preferred direction in Minkowski space, even though, you know, we knew pretty well just a little while ago that there was no preferred direction in Minkowski space. You know, it might be that we need some kind of a new understanding of Wigner's theorem. I don't know what the transitions are that are going to be affected by this, so I don't have specific cases. It seems to me that something weird must be going on, and I think part of the problem has been figured out. Part of the problem was the Halvorson-Clifton translation criteria, but I worry that part of the problem might still be around, and I do not know what the solution to the Wigner's theorem part of the problem is. So that's where I'm at with this right now. Thank you.
Sounds like you have absolutely perfect timing. Very rare questions.
So I just have a really quick question of clarification. So the usual way Wigner's theorem is that it also allows for anti-linear and anti-unitary mapping. So if you have symmetries, you can either get unitary or anti-unitary. But could you say, so I didn't quite get the jump from Wigner's theorem to this thing that you're worried about this transition to be more probable. So if you could just say a little bit more about that. It's just
okay, so the first thing is I'm not distinguishing between unitary and anti-unitary for these purposes. So yeah, every time I've said unitary over the course of the talk, you can substitute in unitary or anti-unitary. That's not a distinction that I'm recognizing for our purposes here. So the way that the problem is supposed to be resurrected, and you know, it's good that you pressed me on this because I'm not really very certain about it. But if I want to know if I have two, energy states of some atom, and I want to know what's the likelihood that one of them is going to jump into the other one, the way I find that out is I take the inner product of the two states. Right? That's a sort of operationalist understanding of the theory's predictions. If that's correct, then generalizing that principle to the case of the magnets, given that some of the so take two states, right, in the plus x representation and the plus and then say, well, I'm going to act on them with a rotational symmetry and bring them over to the plus c representation, right? It's possible by Wigner's theorem that that operation could change their inner product, right? So it might be that the probability for transition between those two states could change just by rotating by some angle. It's, and it might be that the consequence of this is that this transition probability understanding the unit product is too naive. But on that naive understanding, it looks quite bizarre.
I have a qualitative question and a technical question. It's not at all clear to me what your conception of physical equivalence is. I understand the unitary equivalence and the Leibniz equivalence, but I don't understand exactly what is meant by physical equivalence. And before I elaborate on that, let me put the technical question. The technical question has to do with conservatism regarding observables. When we go to the Weyl algebra, the way we do that is we don't like the unbounded nature of the momenta and the positions, so we exponentiate them into unitary operators which are bounded operators, and we generate the algebra that way. And that's very nice. And maybe this question is as much to Laura, yes, there you go, as it is to you. We certainly want the stress energy momentum tensor in some form, just like we want the momenta and the positions in some form. Well, one form is exponentiating. We could integrate the stress energy momentum tensor over arbitrary regions of space-time and then exponentiate it and have a bounded operator that contains the information contained in the stress energy momentum tensor. So the technical question is conservatism really as conservative as it's being made out to be? It seems to me it probably isn't.
Right.
But then if I go back to the qualitative question about physical equivalence, let's consider rotating the infinite ferromagnet. You only know that you've rotated it at all if you rotate it relative to a coordinate system. Okay? Now, mathematically, the coordinate system doesn't require anything else to exist in the universe. But if you really have a physical coordinate system, that concept of the coordinate system is distilling the information about all the other things in the universe that are required in order to give meaning to the coordinate system. And when you say you've rotated the ferromagnet relative to just the coordinate system, you mean physically, and this bears on the question of physical equivalence, that you have rotated the infinite ferromagnet relative to all those other things in the universe required to give meaning to the coordinate system.
That you're not paying attention to
Right,
for that
and
matter.
therefore you haven't done something to which the Leibniz equivalence applies.
Right.
Because, so what would your response to that be?
Yeah. Okay. Wow. There's a lot there. So I should start with the parts that you're not going to interrupt me as much that are less controversial. With regards to how conservative is conservatism, for position and momentum purposes, not very conservative, right? Because, like you said, it's just position and momentum in exponentiated form, and that's totally cool. The stress energy I'm actually less familiar with, but there are certainly cases like particle number where conservatism is very conservative because the Weyl algebra doesn't contain any bounded functions of the total global particle number.
The
Right.
total, to be sure, but
Yeah.
the particle number in any bounded
Particle number is
space-time.
right. So the particle number for a finite subspace. Yeah. It's right. So that it may be. Laura, I'm not sure about. Are there bounded functions of the stress energy in the Weyl algebra?
So, as I understand it, the problem with the stress energy tensor isn't that it's unbounded. But
Just
that
speak up a little bit.
the problem with the stress energy tensor isn't that it's unbounded and that there's some quantum states it kicks out of space. It's that it's nowhere defined, because when you write it down to assign it an expectation value, you've got to take the product of the field at a point.
Even in the context of, pardon the expression, renormalization theory.
Okay.
Okay.
The family of fixes David's talking about aren't affected by
Right.
the unboundedness by exponentiating, because the
Okay.
unboundedness isn't a problem. The
Okay.
family of fixes is constituted by adapting a point splitting recipe for correcting for the way the product of the field at a
Right,
point blows
right.
up by confining attention to a set of states
Yeah.
that all blow up in the same way.
Yeah.
And so adding a stress
Okay,
energy
I see
tensor
your
by
point.
hand. So the example of a different sort from the particle number.
Yeah, right. That would have been my guess, is that it's the same kind of thing that's happening with particle number. But thank you very much, Bob. Okay, so regarding physical equivalence, I was trying not to give a definition of it, but just to give necessary conditions for it. That intertranslatability is supposed to be a very plausible necessary condition for physical equivalence. And the place that Halvorson-Clifton get this is a paper by Clark Gleamore. Well, I can give you the citation because it's on the paper copy of this paper. But, I'll just say that it looks extremely plausible to me that you have to have a bijective mapping between states that preserves all of the predictions, at least for all the observables. With regards to Leibniz equivalence and about whether global rotations are really the sort of thing, or really standing for the sort of thing that we're talking about, right? That's an interesting question, because you might think that whenever I'm talking about a ferromagnet let's say I'm using polar coordinates to talk about a ferromagnet, it may be that what I'm doing is idealizing away from the rest of the universe beside that ferromagnet, right? So that when I rotate the ferromagnet in my coordinate system, that really stands for my rotating the ferromagnet with respect to the rest of the universe. And in a sense, this is a way of showing exactly why we've developed the formalism that we have, right? Because we want a formalism according to which we can represent physical differences between the magnet pointing along plus x and the magnet pointing along plus z. Because if there's other stuff in the universe, then rotating the magnet could indeed create some very powerful qualitative differences between which things are going to go which direction which iron filings are going to pile up where with respect to the magnet. Okay, so the question is it possible to talk about a ferromagnet alone in the universe by itself using a coordinate system in the same way, right? And indeed, one of the assumptions that I made here is that it is possible to work up a solution to quantum theory and say quite literally, I'm only talking about an infinitely long ferromagnet in an empty universe, right? And if you think that's impossible because you think that every, you may think that every use of quantum statistical mechanics or quantum field theory that's going to lead to broken global rotational symmetry is an idealization like that. And if you do, that is a way of escaping my conclusions. I don't find that idea very plausible because, for one thing, I think that one of the things that quantum theory is telling us is that although our world isn't like that, a world with an infinite ferromagnet in it and nothing else is physically possible, right? But if you don't agree with me about that, it still might be that, our universe contains an infinite ferromagnet and a lot of other junk, and I could rotate the infinite ferromagnet and all that other junk together with it, right? So that would be the answer to that question.
Okay, next, Nick, then.
Can I just ask something really quick, and then I have a bit of a longer question. So, this ferromagnet is infinitely long. It's not infinitely wide, right? So then I don't quite understand, of course. So I've got I'm just thinking about it one-dimensionally, right? I've got a whole bunch of little kind of, one-dimensional spin lattice in three-dimensional space. So I've got a state where everything's pointing in this direction. And I can see it's going to be unitarily inequivalent to one where everything's pointing up like this. But of course, I don't expect Leibniz equivalence to hold in that case because it's broken by the shape of the size of the geometry of the bar magnet.
Right.
Or are we not talking? Are we not
thinking
thinking of an
the
Ising?
whole magnet with the.
So it's not an Ising model, because usually in the Ising model, the positions are classical and then there's just spin states. We're rotating the whole thing.
Yeah. So right. So I'm right. There's a sense in which I'm speaking pretty loosely here, because the models that we actually use to describe these things, like the Ising model and the Heisenberg ferromagnet, they have the spin 1/2 systems anchored to the points that they're at. Right. So what I'm talking about is rotate the whole system, including those anchors. If you don't like that, the other thing you can do is just transform the fixed line to the one in which the magnetic polarization is pointing the other direction. The opposite direction from the one that's pointing in the actual world, right? Just switch to north and south.
Unitarily inequivalent?
Those are unitarily equivalent.
So I wanted to come back to this point on your last slide, where you say, okay, is what's going on here that some state transitions are more plausible along plus X than plus Z? And if so, does that? Well, then you said, well, one way you can account for that is by hypothesizing that there's a preferred direction in the Gaussian space, but that seems unattractive. So, my guess is that no, it's not going to work out that some state transitions are more probable when the magnets are reached to 1 plus X than plus Z. But supposing that it were, surely what would then be going on is the following. What we're dealing with is a theory which we would not be able to formulate in a coordinate-independent way on a space-time that has only Minkowski structure. That the space-time would also have to have some preferred direction structure. So the diagnosis of what's going on is not we've got Minkowski space-time and it has a preferred direction as now bizarre. It's we've got a space-time that's like Minkowski space-time except that in addition it has a preferred direction, and there's nothing bizarre about that at all. I think the whole scenario is a bit unlikely, but
right. So that's a much less rhetorical way of saying, So to put the point I was trying to make, we thought we were working in Minkowski space-time, and that was our intention in writing up the theory of this magnet, and it turns out that somehow we deviated from that intention without knowing it or something like that, and that's the sort of surprising fact that I would like to avoid. Right.
I mean, it's not that bizarre. It's quite common that we accidentally presuppose a bit of structure that we didn't realise we were presupposing.
Yeah, I mean, it's what seems bizarre to me is that that broken rotational symmetry has this feature that we would only expect rotational asymmetry to have. So we would expect that. So classically, for instance, in classical physics, I can perfectly well describe a system with spontaneously broken rotational symmetry, like my sombrero with the ball, without leaving Minkowski space. I don't need to do it in a space that has a preferred direction. Right? If all of a sudden, when I go from classical to quantum, I need to start working in a space that has a preferred direction to describe that kind of broken symmetry, that looks quite bizarre. Right? That the difference between classical and quantum would all of a sudden require that broken symmetry requires asymmetry. You know, that would be weird.
Yeah, I mean, I've got a kind of very quick comment, and then a question. A quick comment is just on, well, kind of on this material as well. I mean, I wonder if it slightly overstates what at least Ollie Poole is saying, to say that it's turning out it's just conventional what's going on here. I mean, suppose it's the early 50s, and I'm doing an experiment to check whether there's a pattern violation in some decay process, and if so, which direction it goes. And I've got a gadget here that flashes up a light, green light if it goes in one direction, and a gadget here that flashes up a red light in the other direction. And sure, it's conventional, whether I've written left on this time, it's right on that time, but it's not conventional. I can't show that convention, of course, the red light comes up the green light. Right. Yeah. So I mean, I think there's just exegesis point.
Yeah, I think that's right. Yeah, that's a feature of these slides. I haven't written overly quickly, but yeah.
Okay, this is a certain question. I've shown I lack knowledge on my idea. I mean, in general, in quantum mechanical systems, just because I've got two representations, just because the system has, let's say, the representation of the term of operator included, include irreducible components, it doesn't automatically follow in general that those irreducible components are unitarily equivalent. I mean, if I take, say I take a spin half bundle, Z, just take a bit, and then the not speaking from internal degree of freedom doesn't couple to the Spacetime symmetries, and I've got two infinite sets. So what exactly are the properties in a QFT that are coming into play to guarantee that any two irreducible representations are unitarily equivalent?
Oh, you mean well, that's going to be a case-by-case question. What's coming in? So it will sometimes happen that you have a reducible representation that's a direct sum of the same irreducible representation itself, right? Yeah. Yeah, that's called a factorial representation. Yeah, and so the question is, why aren't these magnet situations like that?
It's not very obvious to me that. I mean, sure, if I transform, if I take, to avoid mixed concern, let me make that three-dimensional fill for the whole space, and I do a rotation of it. Yeah. And it's clear that I'm going to get a different representation.
Right.
And I'm not going to be able to find, it's not the case that one of those states is the other one, but it's not clear to me why I can be confident that the two representations are equivalent. I mean, precisely because of your point about the allowed things there.
That's an interesting question. Right. Yeah, I mean, so part of what's going on here is that I do not certainly, and at the end I think I was judging from this, I don't understand what the physical differences between the representations are supposed to be. That's completely opaque to me at this point. So the fact that there are, different sectors that are parameterized by different values of the, we might say the symmetry breaking order parameter, right, which is the in this case, the magnetization vector, is usually what people cite to say, there's a physical difference between the unitary and the equivalent representation. Why that should be a difference that makes them unitarily equivalent, as opposed to unitarily equivalent but standing for, in some sense, like locally different possibilities. Yeah, that's a good question, and one that I do not, I think that question is going to be, if I had to guess, I would say down that road lies maybe the solution to all this. That maybe something is coming in with unitary inequivalence, quote unquote, that you can, in some sense, describe as still like a notation variation.
But I mean, it was not careful with potential circularity. There was something like, well, the representation A and representation B differ by the following parameters.
Yeah.
Therefore, physical claim. Therefore, mathematical claim, it must be unitarily equivalent. Therefore, physical claim, it must be the case that we can't do a Leibniz trick to regard those being the same physical possibilities like mathematical difference.
So given the places this is coming from, I would be surprised if the confusion that basic were
I'm not really attributing that to anyone, I'm attributing that to, well, except myself. That's kind of
That's what David meant. I thought you were describing it to me. But no, I guess that I guess I can say that's extremely helpful, and that's the sort of next direction that I would like to see this go. So I hope that's what's happening.
Wayne, you're next.
Is there an easy way to get an intuitive sense of wherein the unitary inequivalence of rotated states of the ferromagnet consists? Because well, first of all, is it okay to imagine the ferromagnet as a line of equally spaced spin? Is the way I think we're talking about it.
Yeah.
Okay, so if I take that along the z-axis, there's going to be stable states in which all the spins are pointing in the plus z direction. If I rotate the thing, there's going to be no stable states in which everything's pointing along the z direction. But surely that's not just what we're talking about, because we rotate the stable states too.
Yeah.
We rotate the observables too. So what is it that's different between those two systems? Different about those two representations? And actually, let me put it a little sharper. Any two Hilbert spaces of the same dimension are isomorphic.
Right. That's true. Now, I mean, isomorphism isn't.
Isomorphism is not the same as unitary equivalence.
It's clearly not the same as physical equivalence,
Yeah,
because
clearly
different
not the
Hilbert
same as
spaces
physical
can describe
equivalence,
different theories.
What prevents? But what's physically? So, suppose I guess take an isomorphism between the two things. What has changed physically there?
Laura looks like
Laura
she
wants
has
to
something
answer
to say.
Yeah, can I try?
Yeah.
So what we care about is a map. We're doing quantum physics.
Right.
You've got your spin lattice.
Yeah.
You've represented Pauli observables each side.
Okay.
And what we want for your representation of the polar emissions to be physically equivalent to mine is a map from your Pauli spins to my Pauli spins that extends out to the whole algebra of observables we care about in such a way that for any state you entertain, there's a bijection from your state space to my state space, and a bijection from your observable set to my observable set, such that the image of your state acting on the image of your observables. And simply noticing that the Hilbert space are of the same dimension doesn't guarantee that
Speak up just a little bit.
simply noticing that the Hilbert spaces are of the same dimension doesn't guarantee that there's a map starting with the canonical observables and spreading out.
But intuitively, why does that fail for rotating
Okay,
magnets?
there's this subtlety that arises when the story changes from representing Pauli observables on finitely many spins to representing them on infinitely many spins. Here's a sort of boneheaded way to represent the Pauli spins for finitely many spin systems. Take your Hilbert space to be spanned by maps from the points in the lattice to +1 or -1. These correspond, say, to spin up or spin down and spin z. Define spin z that way. Okay? Represent the rest of the Pauli spins in that way. The subtlety that arises when you try to extend that model to an infinite spin chain is that you're building your basis, if you boneheadedly extend the model, out of a set of maps from infinitely many lattice sites into +1 and -1. And that set of maps is non-denumerable. You're talking about a non-separable Hilbert space. Okay. So to act in good taste and do your physics in a separable Hilbert space, you've got to find some way of cutting, same general model, of cutting down the number of basis vectors. So here's a way. I'm going to start with a basis vector that is the map that assigns every point, every spin, the eigenstate, spin z up. And then I'm going to add as basis vectors maps that differ from that map in finitely many places. Okay, so far. And then you can represent the Pauli spins in a natural way, and Bob's your uncle. Think about how the global magnetization behaves on this representation. And every basis vector, because every basis vector in this representation is only going to have finitely many spin z downs. And every basis vector in this representation, the global magnetization is going to take a value of 1 in the z direction. Do you believe that? Just because of what I had to do to this. Okay. So that's your theory. My theory, I just copy your theory because I'm very lazy. When I flip everything over. So in my theory, the basis vector I start with, everybody points down. And the other basis vectors are basis vectors that differ from that one in finitely many places. So in my representation, the global magnetization, the global polarization on every state is going to take value -1 in this direction.
Why can't I take every observable on the first one and just sort of rotate it and then it'll look the same on the other one?
You can do that, but what you're going to, so that seems like the way to preserve the isomorphism from your observable set to my observable set. But then when you find, let me add one more thing. In your representation, magnetization is like the identity of something. It's going to take the value 1.
Okay. So it may be, I should just say.
So you can do that, but then in order for my representation to be unitarily equivalent to his, there's got to be a state in my representation that assigns the counterpart of his magnetization, the same eigenvalue, the same expectation value states. But his states all assign magnetization eigenvalue plus 1 in the z direction. My states all assign it -1. So the unitary, the putative unitary map maps the identities of observable to minus the identity of observable.
So maybe the identity isn't a physical observable.
Well, it's a global magnetization.
Okay. I mean, so what it sounds like is we do have a translation scheme that's not unitarily implementable.
Right.
Right.
Yeah,
Exactly. That's the.
And so the question of the identification of unitary equivalents and having a translation scheme.
Yeah, I mean, definitely in the Clifton Halvorson case, they did it for a bad reason, right? Yeah. Now in the Wigner theorem case, I wonder what the bad reason is. I just wanted to say, sorry, but also adding up on something that Laura said. I mean, it may be. I've often wondered why working in separable Hilbert spaces is, good form. I know Tracy Luper will agree with me about this. It may be that assumption that went in there is a mistaken assumption in some ways, that if you were to really do it in a non-separable space,
That's here for reducible representations.
No, I've got the order. Hillary, then Gordon.
Well,
and
scratch me, because I was just going to add a comment to what Laura was saying, and it doesn't have to be added. Sorry, I didn't want to confuse.
Okay, Hillary.
Yeah, I mean, that's just throwing that things back to what I was saying. Like, he'd want an immediate answer to my, well, couldn't maybe unitarily equivalent after all. At some level, what we may clearly no, because no unitary map is going to take I e to the minus. However, from the point of view that's worrying you, which is like breaks and transition amplitudes, that's not going to be a problem, because there's going to be a map, there's going to be a unitary map that gets the states right, that is getting you into trouble with the observables. And I think that is that's going to be fine, because we're happy with the fact that, as you say, we don't want to do that as a house reason. But we're still going to take the states to the states unitarily, and we're still therefore going to preserve translation.
But you know what, in this case though, your problem is going to be that the problem with the observables is going to be exactly the observables you need. It's going to be with the spatial translations.
Oh, I've got no problem with those observables. I mean, let there be documentation. Let those things be there by all means. And sure, acknowledge that the map between them is not going to take an observable to the same observable. Or going to be a unitary map of that kind anyway, and feel relaxed about that for exactly the reasons that David gave. But don't worry about the fact that transition amplitudes are doing something that seems physically unacceptable, because they're not, because the map we're carrying out is unitary on the states. It's just not. It's just the rules for going from the operators in this space to the operators in that space are not use the unitary transformation you just used. There's something like use that transformation and then apply a line that shifts to the defining parameter.
Right. Okay, good. So then in that case, the problem would be basically the assumption of the Wigner theorem that we are doing the same transformation on the observables and on the states at the same time. Yeah.
Thank you.
Yeah. Right. Yeah.
Okay, Nick?
So, but maybe the things we're saying here are kind of an artifact of the model, right? I mean, maybe there are more robust kinds of unitary inequivalence where the energy levels are different or something. I mean, the ground states are related by spatial symmetry, but the energy levels are different. There really are, there's no mapping from the transitions, or transition for amplitudes or something.
It's going to be spontaneously broken symmetry. That sounds like you actually have just intrinsic different states of balance.
So, okay, if you had examples like that, then their argument gets
Yeah.
going again, right?
I mean, that would be the kind of example that would be extremely surprising, right? But I mean, part of what's happening here is that I know these global formal properties of the example, and then the sort of local, minuscule, microscale properties of the example are supposed to undergird them and things that have been kind of opaque. So, yeah. So I'm not sure. If you look at broken symmetry states in quantum field theory, for instance, which you get with quantum optics, you have a coherent state that's propagating along some direction or something like that. In that case, would you have a situation where you actually had a transition into that? You know, I would be surprised if it wasn't similar to this.
When you get particles with different mass ratios and things like that, I mean, mass comes from...
Yeah, actually, a comment on that. Broken symmetries were first discovered in condensed matter physics. It used to be things like ferromagnets, etc. But then the applications that were made of them to high energy physics, relativistic quantum field theory, and that we hear so much about these days, there, that Mexican hat that you had doesn't exist in space-time at all. It exists in field space. It's like a potential energy function over a field space where you're dealing with a field, essentially the Higgs boson field, that doesn't have any variation in space-time. It's just a constant everywhere in space-time. But you're wondering what its value will be. And there, as the field value rolls around trying to select a place in the rim of the hat, selecting a particular place does give rise to values of other parameters in the field which in fact determine mass ratios ultimately. And so one reason for mentioning that is ask, to what extent do you think your considerations would apply to a situation like that in which the symmetry breaking isn't taking place in space-time at all?
Oh yeah. I mean, for internal symmetries, you know, I certainly don't think that there's obviously a consideration like Leibniz equivalence, which indicates that they have to always relate the same physical possibility. It would, in some sense, be nice if that were true, because we could have a nice unified model of what symmetries are doing. But you know, looks like there are cases like the one you described that it's just going to look extremely attractive. So, are we out of time?
One thing to mention is there's going to be a panel discussion at the end of the day where we have a chance to ask further questions about each of the talks during the day. So I think we might stop now and hold further questions for the panel.
Thank you very much, and especially for all the good questions. Great.